Okay, so anybody have a guess what this is? Yes, what is it? Yeah, let's see, I think that's the cochlea there, but what I'm guiding your eye towards, the thing relevant to us is this. Look at these three loops. That's your vestibular system, I think is the word. You have a Cartesian coordinate system in your head. Look at this. This is why we prefer Cartesian coordinates. This tube detects you doing this, and this one detects you doing this, and this one detects you doing that. And it's actually like Cartesian. That's why we like Cartesian over rotational or spherical. That's my theory. I don't know if it's true or not. But this really is in your head, right? That's an MRI of, that's actually my, no, it's not. Rather than just look it up on the internet, I went and got an MRI and, because I'm really dedicated and, Okay, so this has all been kinematics. Right? Now we got to do dynamics. Now we got to figure out what's the force that's going to cause these things to go around. Okay? And yes, everybody pointed out I didn't calculate alpha. So since it was uniform circular motion, alpha was 0. We didn't have it doing angular acceleration. And that's sort of a question of how much we're going to really cover that. We're probably going to focus on uniform circular motion. I'm going to try to get to it a little bit in the lecture, and on the homework it's unclear yet because I haven't finished the homework. Okay? All right. Let's see. I can't write the homework until we do the lectures, but I can't do the lectures without writing the homework. It's like Chegg. I should start a company and take people's money so they can cheat. That's what Chegg is, chicken and the egg. A bunch of guys high in their dorm room. Dude, is it the chicken or the egg? Let's make a website about it. Okay, circular dynamics. Okay, basically all we're talking about here is a net force must cause, I'll say, AC, right? By Newton's second law. The sum of the forces in the centripetal direction must equal the mass times the acceleration in the centripetal direction. Now things are rotating. It sounds weird, but it'll be fine. You're going to be okay. You might not be okay if you get out of your seat, though, okay? You guys in the front. Let's all make eye contact. Do not get out of your seat right now, okay? Because this might hit you in the head. And I didn't register this party, so. Okay, so a conical pendulum is basically one that hangs at an angle, and then you give it a little sideways motion, it goes in a circle. Do not get up. Stay where you are. Look at that thing going in a circle. Very beautiful. It doesn't look dangerous, but you don't realize how heavy it is, right? Ow. Right? I mean, it will hit you pretty hard. There was once an unfortunate news story, really happened not too long ago, where like somebody working on a site didn't know a lot about the big balls that knocked down the building, and one was moving slow, and the person thought they could stop it. And they died. I mean, they got between it and the wall. And they just had no intuition. So things that are heavy moving, you should stay away from them. Like a car is the only exception; it has airbags in it. Okay, so conical pendulum is basically just this situation. We have this big mass hanging down, and it's going in a circle. So I got to do 3D drawings now. And then here's like the normal direction, like that. And I'm going to call this angle phi. Okay, I'm going to call it phi because theta, we've been talking about, is more like this angle going around the circle. Phi, or phi, what Chegg charges to help you cheat, is another way of saying it. I don't know what Millie's music video is, so I don't know. I don't know who Millie is. Millie is Millie Dresselhaus, who I knew. That's the only Millie I know. So we got to think about forces. Let's just think generally what's happening. Is this cable under tension? Yes, it is. I can feel it. It's like ready to snap. It's like us, right? It's under tension. So we have a tension force up, and we have like the weight pulling it down like that. Right? But how does that make it go around? We give it like an initial velocity, kind of like that. Right? If I just hold it at an angle and let it go, it doesn't go around. Right? But if I hold it at an angle and shoot it to the side, it goes around in a circle. I can make bigger circles, but I'm not going to. When I'm in here alone, we have huge circles, but I'm not here alone. Okay, so this is now dynamics. We have to think about forces and what they do, so we need a free body diagram. Right? So here it is. Here's the mass. And in these dynamic problems with something rotating, you kind of have to think about how to do your axes. If you think about it, it's moving in a way that VT keeps changing. That'll be annoying. The centripetal acceleration keeps changing. That's annoying. So you just kind of pick a snapshot. That's why I kind of drew it on the side here. So we'll say in this snapshot, we'll consider this y, and we'll call this centripetal direction. We could call it x, but I like to call it centripetal to remind you that we're not just doing xy kinematics. We're actually doing circular motion. Okay? So let's go ahead and draw it that way. mg is down. All right. And since you guys are like trig ninjas at this point, I'm going to not draw the full tension. I'm going to draw the components because we need the components, right? So there's a component of tension that way, and there's a component of tension that way. And let's say which trig identity, oh, it's this component sine. Oh, but the angle's in the wrong place. So you've got to be really good at trig now, right? So if I want this component, normally that's the cosine because it's to the side, it's the adjacent to the angle. But when it's the opposite angle, you just switch sine and cosine. So this is t sine theta. Notice how I look at my notes as I walk. Do you ever catch me when I do that? It's clearly t sine theta. Okay? Now, this one over here is clearly the opposite, is the vertical one, which is normally sine, but because we switch, it's cosine. T, cosine phi also. Okay, let me stop screwing around and mess you up here. So this component is t sine phi up, or phi. T is t cosine phi. So there's our free body diagram, right? We have two opposing forces in the vertical, and we have a constant force to the right in the centripetal direction, right? So let's see what we're going to learn. Vertical. Sum of the forces in the y must equal, is it moving in the y? No, right? It's perfectly level in the y, so it must be 0. It's not accelerating in the y. So t cosine phi minus mg, the weight, equals 0. So this is how you get the tension. Right? The tension, if you want real quick, is just the weight divided by the cosine of phi. It's not times the cosine of phi. Okay? If I get this thing at a really big angle, it needs a huge tension because only the vertical component is holding it up, and the vertical component at a big angle gets really small because phi goes to 90. Okay, so now let's do the centripetal direction. This is where the excitement happens for the conical pendulum here. So there's only one force, t sine phi. And what is it equal to? The mass times the acceleration, but what is it? The centripetal acceleration. If we're in uniform circular motion, the only acceleration is the centripetal acceleration. So there it is. And also we're considering this direction, so that's the only one, is the centripetal. So you say t sine phi equals the mass, and what is the centripetal acceleration? Well, we're thinking in terms of giving it a vt. I'm sorry, we're trying to find, I didn't really say what we're trying to find. Find vt as a function of phi. That's what we're trying to do. Or get some relation between how fast it goes and how high I hang it up. Because you'll notice if I have a very small phi, this is what I forgot to say at the beginning, it's kind of a slow vt. It's hard to get it to go in a circle. Small phi, it's moving kind of slow. Here, if I come this way, I believe it can't possibly hit you. Not sure about that, though. Might take out my computer. And a big phi, it's moving much faster, isn't it? Oh, okay, see? That's what we're trying to find, is how does vt depend on phi? Okay, so I forgot to say that at the beginning. So let's start over. No. So we do free body diagram. Vertical gets us attention. This one is now AC, so it's vt squared over r. Right, so vt is the thing kind of we're trying to solve in terms of phi. Okay, but tension is also unknown. Between vt and phi is what we're dealing with. We know the mass, we know gravity, but we don't really know the tension, so we want to plug this in for the tension over there. There has to be two signs show up. Oh, it's vt squared. Oh, yeah. Yeah. So the tension is mg over cosine phi. mg over cosine phi times the sine of phi equals, I remember, m vt squared over, what about the radius? God, I screwed this up. I gave you the length. It's a conical pendulum of length L and mass m. I should have written this out as a problem. It's a conical pendulum of length L and mass m. You hold it at an angle phi, how fast does it go? That was supposed to be the problem that I forgot to write down. Okay, so we've gone through the whole thing. We don't know the tension. We don't know R, but we know L. And there's a triangle here. All right, so If we do our SOHCAHTOA here, we can write it all out. Sine phi is opposite r over L. And you see, oh, it's not a component. We're actually getting the short part. L is r over sine theta. Or r is L over sine theta. So we put, I'm sorry. Okay. So we have r here. mv squared over r. It's going in a circle this way. And we want to write it in terms of something we know, which is L. Right? So r is L sine theta. Thank you. L sine theta. Let's see. It's a good time to stop for a question, because I can't do trig anymore. Oh, you have no idea what's heading your way later. Okay, so we're going to solve for this. So we're going to cancel the mass. And this is just a huge bumbling way to get to VT. So we found that VT squared is what? I can't even do it anymore. G times L. All right, times what's left? Sine over cosine is tangent of phi. Good Lord. Tangent of phi. And then we bring up another sine of phi. That's actually the answer. It's not pretty. Okay. Almost worked it backwards. But that's the answer. So what this tells us is, does this increase? Is it what we expect? For a really small phi, a really small angle to the top, is it slow? And for a really big angle to the top, is it fast? Well, let's have a quick look. What we got to think about, what I want you to be able to do, what will help you do problems, is to be familiar with the shapes of your trigonometric functions. All right, so if here's phi, I could plot tangent. If I go out to 90 degrees, probably the biggest angle I'm going to make is 90 degrees. This thing will be going really fast, potentially, because the tangent looks like this. And it goes to infinity here. Oh. Right? So that term goes to infinity at 90. That's tangent. If you've never seen it before, there it is. And sine, what does sine look like? Sine is 0, and sine kind of goes like that. Right? You know what sine looks like. Okay, I must have written my tangent wrong. Will all the box equations be given on the exam? Probably, yeah. What is the L in the last equation you wrote? L was the length of the pendulum that I forgot to give at the beginning. Do you mean phi instead of theta? Yeah, I changed it, yeah. Okay, but let's think about these functions. We're multiplying sine by tangent. That's all we're doing. So what is the product of sine times tangent? Well, you know. Right, if this is still 90, so we can see if this answer makes sense. The product of sine times tangent right, is what? It starts at 0. It kind of increases together, but it still goes to infinity. Right? So if we ask ourselves, does it make sense with the world? Then yeah, it's really slow. It starts at 0 with no angle. It doesn't move at all, and it gets faster and faster. Then imagine what it would take. Now, I could do it over your heads, like if I got way back here, but I won't, right? Imagine what it would take to have this thing at like 80 degrees. It would have to be flying really fast because it would have to be able to cancel this vertical force. And as phi got really big, cosine would go to 0. Basically, there'd be very little vertical component left of the tension to cancel gravity. So the tension would have to be huge so that the little cosine component could cancel it. And if the tension is huge, then the thing goes really fast. Okay? So it makes sense. Okay, so that was just supposed to be a simple example of using a force to figure out a circular motion problem. Okay, the conical pendulum. And it did something that you're going to have to be able to do in these problems is to think a little bit in 3D. Right, we had an angle this way, and we had something going around that way.